All right. Thank you everyone for joining this week's Landscapes Live seminar. We are very happy that so many have tuned in again this week. And my name is Vivi Petersen and I'm chairing the session today. And then we have also Philip Steer and Steffi Tofelde as the moderators. And today we have a very special seminar in the honors of Patience Cowie that unfortunately passed away earlier this year. And I've been lucky myself to know Patience and interact with her during my time as a postdoc in Bergen. And she's been a very good role model for me and for others, I have to say. And today we are lucky to have Alex Whittaker from Imperial College of London and Mikael Attal from University of Edinburgh to honor Patience and her great scientific achievements. And the title of the talk today is Folding and Landscapes, a tribute to Patience Cowie. And after Alex and Michael's talk, you're all welcome to ask questions, add comments, and share your experiences with Patience in the chat that we will open in the end of the talk. And you're also welcome to raise your hand in order to use your microphone. So with this, I'll just simply give the words to Alex and Michael. So if you will unmute yourself and share your screen.
Thank you, Vivi. Hi, everyone.
All right, I hope everyone can see this.
It's good.
Cool, brilliant. All right, well, it is a real honor for Mikael and me to give a talk on faulting and landscapes as a tribute to Patience Cowie, who we both worked with closely and who made a huge difference to our careers. So, you know, Patience had a long and distinguished career, starting obviously with a bachelor's degree in Durham, and then moving to do a PhD in Le Mans with Chris Schultz, and then via Nice she came to Edinburgh, and then finally to Bergen. If we were going to describe her contributions, we might say that the first half of her career really focused on the seminal work that she did in terms of fault growth and interaction, and that has made a huge difference across a number of communities. And then, if anything, her career had a second avenue where she then moved towards thinking about landscape responses to active faulting. So this seminar will talk particularly about that second part of her career in a way, but we'll also talk about her early work on faulting and fault growth, because I think it's really important to understand the context of where she was coming from with this, with her work. So I obviously did a PhD with Patience, and I moved up to Edinburgh to work with her in 2002. And you know, I can honestly say that working with Patience was one of the most inspiring and challenging things that I've done, and it completely revolutionized me as a scientist. And then, Mikael, you might want to say a few words about your experiences as a postdoc.
So I joined the team in 2005 for a postdoc, and then I didn't leave Edinburgh since then. But I would echo what Alex said. Like, working with Patience was just fun and completely changed the way I was thinking about science. And it's been great to interact with these people during that project and then interact with them as colleagues afterwards.
So we will say a few more words about our personal recollections at the end of this talk. But in terms of what we're going to present here, there's really three parts. The first is in terms of fault behavior and the insights that led to Patience's work in the Apennines, to which we were all contributed. Mikael is going to talk a little bit more about that Apennines project and what the experience was like. And then we're going to pick a few avenues that work, research that came out of that. And there are many, many of those. And we've just picked a few that interested us. I think any talk about faulting and Patience Cowie can't take place without reference to this diagram here, which is actually a diagram showing the maximum displacement on faults against how long they are. And Patience's initial work really succeeded in explaining two fundamental things that we know about faults. One is that faults have predictably larger displacement when their lengths are bigger. And the second is in terms of the gradient of displacement from the center of fault to the tip. And what Patience did in some really amazing work with Chris Schultz was to use a plane strain model of faulting and include the inelastic behavior towards the tips of faults to actually explain this kind of distribution. And it's not what you would get if you just used an elastic model. So actually, understanding why it was that we got this kind of behavior in faulting was like a huge thing. So that physical explanation for two key observations of geological faults was then coupled to further understanding about how faults grew and interacted. So this paper from 1998 really explained how it was that faults grew together and interacted. And essentially what Patience showed was that, if you stretched, say, part of the crust and you nucleated and grew faults, then as you had particular earthquakes on one of these fault segments, then it could stress optimally located faults, for example, along strike, and bring them closer to failure, whilst other faults might lie in a stress shadow and be taken further away from failure. The effect of that was to basically enable some faults to grow and interact and get larger and therefore have bigger displacements, while some faults died and became inactive. So this was a really powerful way of thinking about how faults developed. So when we talk about this kind of thing, we often talk about, for example, faults which are hard linked, by which we mean that individual fault segments, for example, this one here with length 1, join together to make a new fault with length L2 in this case. And what Patience was able to show was that, in fact, as these faults linked, those segments that were located centrally would undergo a predictable enhancement of their throw and throw rate. And indeed, you might get those effects even if the faults were not physically joined, as long as their stress fields were interacting, so that this segment here realized the presence of the other ones around it, and therefore the rate would increase over time. So her modeling showed some of this behavior, but one of the key questions was, of course, can we find evidence of this occurring in fault arrays? And actually, this is where the Central Apennines came in, originally with work with Gerald Roberts as a lab, if you like, to test some of these ideas. So the Central Apennines, I've been working there for coming up 20 years now, which scares me massively. So this is an area of active extension, something like 4 millimeters a year of stretching is accommodated across here. And there's a network of active normal faults that are approximately 3 million years old. And it's also an area, this is elevation, distance across the strike, of elevated topography. So this fault array was one place to go and look at some of these ideas of fault growth and interaction. And one reason why this was a great place to do this was because we had good idea about how rapidly these faults were moving. And the way that that is known is from things like this. So this is a fault scarp. This is the Velino-Magnola fault. This is Monte Velino. This is a retro picture of me up one of these faults. And one of the things that we know about, or we have reconstructed for this area, is that, you know, at the last glacial maximum, hill slope processes were more intense. And that meant that, you know, any earthquake that uplifted this footwall of the fault, erosion was, hill slope erosion was intense, and you basically did not build a fault scarp. From the late Pleistocene to the Holocene, as we've gone into the post-glacial period, the efficiency of those processes have declined, enabling a fault scarp to be built up that offsets these late glacial hill slopes. So they look a bit like this. And of course, if we can measure the throw on that fault scarp and the offset from a slope that is approximately 15,000 years, we can get a rate. There's some work that Gerald Roberts originally developed. And of course, these are originally measured using something long and straight like a broom. So it's actually, you know, so these are really good data originally. And what Gerald and Patience really were able to look at was to compare, for example, what the prediction of throw on a bunch of these faults in the central Apennines. Let's take the Fucino fault. This is distance along strike and its throw. Given that we know how fast the faults are moving now. So if you took, for example, the throw rate now and multiplied it by 3 million years, you'd expect that these faults to have something like 6 kilometers of displacement. But of course, they don't. They are under displaced for the length of time they've existed, given the throw rates that we understand. And what Patience was really able to show was that that was in effect because the faults in the center of this array had increased their rate due to fault growth and interaction. So the Italian Apennines were a natural laboratory to evaluate many of the modeling contributions that Patience had made. So that fact that the Central Apennines show this kind of behavior was really where Patience was originally coming from. The landscape dimension was something that came after that. And it's quite interesting the way that that did come. And I was speaking recently to Greg Tucker about this. So in the early 2000s, geomorphologists who not necessarily thinking about active faulting, but thinking about how landscapes, and particularly rivers, might respond to changing uplift, had developed the idea that whilst many river-long profiles, regardless of erosion law, looked relatively similar at steady state, if they were perturbed by a change in uplift rate, then something like rivers that were governed by a stream power erosion law should have a diagnostic erosional response. And that was laid out in a couple of papers by Kellen Whipple and Greg Tucker. And one of those diagnostic erosional responses was the development of a nick point. So this is elevation against downstream distance that would propagate upstream and would transmit the signal of relative base level change to the landscape. Now, models theoretically showed that this is how this advective wave should behave, but we didn't have examples in reality to demonstrate that. And it was fun to go back and read some of these papers. I pulled out the figure caption from figure 11 here, a possible example of wave-like transient response to an accelerated rate of base level fall. And we take it for granted often nowadays that, you know, like a nick point might represent, for example, a change in slip rate on a fault. But of course, you know, where we were starting from, we didn't know that at the time. And of course, that really raised the question of if only we had some good field examples where we knew what the fault slip rates were. And this is where Patience actually hooked up with Greg Tucker to actually answer this question, as Mikael will explain.
Yeah, so here we are in 2005 in the Apennines, and Patience got a project funded by NERC to specifically look at the signature of these faults on the landscape. So the team was made of Patience. Here we've got Gerald Roberts, who is here, who had a very good understanding of the faults there. Greg Tucker, who was bringing the numerical modeling aspect. A young Alex Whittaker as a PhD student, whose project was eventually called Investigating Controls on Bedrock River Incision using natural and laboratory experiments. Nate Bradley, who came as a field assistant at the time, and myself as a postdoc, and my project was called Testing Fluvial Erosion Models using the transient response of bedrock rivers to tectonic forcing. And the idea was really to like building on this background theory and this understanding that the faults in the Apennines have had some very different history. We are thinking, okay, can we look at the landscapes in the Apennines to try to understand things, to try to identify these diagnostic features that will tell us about the tectonic history of faults, so we can do tectonics from topography, but also will validate these models that have been proposed in the past few years. So the approach was really a combined approach, and we were going to use a fieldwork, topographic analysis, and numerical modeling, with Alex's project focused on the fieldwork part, and my project focused on the numerical modeling, but they were really complementary approaches. I'm going to start with the fieldwork, and here an introduction to the. So that's when we arrived in 2005 in the Central Apennines, and we were introduced to the beautiful landscape. I mean, these are really, really big mountains, steep mountains, tectonically active, and you can sense that in the landscape. We were introduced to the tiny cars in the Italian countryside, like the Mattis, who took us around for a whole month, which was brilliant. But people were looking at us suspiciously when they saw a big man in tiny car getting into their village where there's no tourists, typically. We were introduced to the wonderful countryside accommodation, like the Filippone Hotel here. Like people were wonderful in terms of welcoming us into their agriturismo and so on. It was a wonderful place, but what was really incredible as well is to see how this tectonic activity was present in everyday's people's lives. Like, this is the fault scarp of one of these active faults here, and you could see it from the back window of your hotel room. And everywhere we've been, people had fault scarp in their back garden and so on. So it's really like, we really got a sense of how active this place was. And you had the evidence of this faulting in the last 15,000 years, essentially preserved everywhere. So I'm going to show you a couple of examples of that with the field work. And of course, we had to touch our first fault scarp, which was this one here. And I was just amazed by how perfect these scarps were. I mean, they were continuous for kilometers across the landscape, and they really made these big scars across the landscape. And you could really see how over the course of geological time, how cumulative effect displacement on the fault created the mountains that we can see now and the sedimentary basin. The scarps are really nice and polished, and you can really, when you start thinking that all that happened in the last 15 to 18,000 years, it is very spectacular. And what we have here is a place where a French team, I think Palombo and Benedetti, have been sampling for cosmogenic nuclides. So they've been sampling the fault scarp at different elevation all along to try to understand better if we can date the exposure of different parts of the scarp. We can understand better the seismic cycle and so on. That idea was then pursued further with Patience, and Alex will talk about that near the end. But most of the work that we were doing was really going to be focused on the rivers, and the field work was really dedicated to measure the things that we cannot get from a digital elevation model, like, for example, channel geometry, channel width, canal slope, and also the characteristics of the sediment that these rivers were transporting. So we had these rivers and we had these very spectacular gorges that even LiDAR data now would not be able to resolve. But you know, everywhere we had evidence of this active incision where the rivers were flowing across this active normal fault. We had evidence, very clear evidence of active incision into bedrock as shown here. We had a topographic analysis component, and again, that's something that has exploded in the last couple of decades, but we now take for granted that we've got a digital elevation model, LiDAR data from all these parts of the world. But at that time, like, we had just got a 10-meter resolution DEM of this area, which doesn't sound amazing, but at the time, I mean, what we were dealing with was essentially 30-meter Aster data, 90-meter SRTM data, and here we had a 10-meter resolution DEM, which allowed us to really get in a much greater amount of detail the river profiles, the profile of these rivers, and the morphology of the catchments that were draining across this active normal fault. And what we were interested in particular, because all that was about transients and whether we will see the evidence of this transient in the landscape, was to extract the river profile from rivers that had different histories. So we had rivers flowing across faults that had become inactive, like the dashed one here. So this fault had become inactive. And we had the rivers that were flowing across faults that had moved at a constant slip rate since their initiation. So the faulting in the Apennines started around 3 million years ago, and then carried on and is still carrying on as of these days, as is shown by the frequent earthquakes that are happening in Italy. That is one of the most tectonically active area in Western Europe. And some of the faults have been moving at a constant flow rate all through their history, which are shown in blue here. And some of the faults have accelerated, like the faults here in the middle of the array, have increased their slip rate around 1 million years ago due to fault interaction and linkage. And we were looking at the profiles of the river that were flowing across this fault, try to see if we had any evidence of this transient response to increase the slip rate. And then finally, we had that numerical modeling part. And I'm going to start presenting that with some results of some work that the patients had initiated before the start of the project. And it was really trying to link the tectonic model that she had developed with a surface process model to see how the interaction between the fault, to get a sort of generic understanding of how the fault development and interaction and linkage was going to affect the geomorphology of this area that are experiencing extension. What I'm showing here is the tectonic, the fault offset accumulated over 4.6 million years here. So this is before fault linkage. There's no topography involved, there's no erosion involved. This is just to show the offset of the fault. And in the early stage, so this is extended in that direction. And in the early stage, you have a lot of small faults that are active everywhere in the landscape. And then the faults in the middle here start interacting, and then most of the flow is focused on these faults. And at that point, you can see that the uplift, the relative uplift increases here, and you create a greater topography as a result of this increased flow rate on the faults here. What that means for the topography and the organization of the catchment, what we see is that in the early stage, what we have here is the sediment volume as a function of time for these catchments that are exemplified here. And what we can see is that in the early stage, where we've got weak to moderate fault interaction, we've got a lot of like switching around in terms of sediment flux, size of catchments. But then from the moment you have that strong fault interaction, the river network become set in stone, if I may say, and suddenly the sediment flux increases because we are increasing the uplift rate on the fault, and the river network, like water and sediment, are being focused through the place where the offset was the smallest at the time of the linkage. So clearly what patients' work showed is how in the early stage, you have a lot of competition between catchments, and it's really in the later stage when you link the faults that uplift increase, sediment flux to sedimentary basin increases, and you carve your river network and keep it constant for the foreseeable future. So that was the generic insight, but what we wanted to do, something that hadn't been attempted much at the time, was to try to reproduce the evolution of real catchments. So what we started to do is we used the channel hill slope integrated landscape development model, which had been developed by Whittaker and colleagues like Mikael, for example. And we took some of our real catchments and turned them into triangulated irregular network to try to see if we could reproduce their evolution through time and their morphological features in response to different tectonic history. What we wanted to do in particular is test the fluvial incision laws, see if detachment limited was doing a better job than transport limited, for example. We wanted to test the influence of threshold for erosion and also the influence of dynamic channel adjustment that Alex is going to talk about later. So that was the model setup. For here we have the Rio Torto with the Fiammignano fault. We've got the uplift rate that is constrained. We've got back tilting with distances of around 10 kilometers between the fulcrum and the fault itself. And that was constrained by field data. So what we did is looked at the evolution of this catchment. With here, what we started with is we know that the Fiammignano fault increased its flow rate from 0.3 to 1 millimeter per year around 1 million years ago. So we tried to replicate that. And we started with a topography that was in steady state with the uplift rate of 0.3 millimeter per year. And then we increased this uplift rate. So what we have here is the two river profile, the blue and the red. We've got the uplift, we've got the fault. And as we increase the uplift rate, what we see is this signature that is very distinctive that most of tectonic geomorphologists are familiar with here. You've got a nick point that's propagating upstream. Downstream of the nick point, we've got a steep ridge that has adjusted to the new uplift rate. We've got a greater erosion rate in the lower part of the catchment. And that happens while the upper part of the catchment is being passively uplifted. In that case, because there is back tilting as well, what we have is the gradient of the river is progressively reduced to the point where you can have drainage reversal, as is shown here. The slope becomes negative, and you end up with this internally drained basin that we can see evidence of in the Italian Apennines in quite a lot of places. So these processes seem to be effective there. These internally drained basins can remain internally drained, or they will eventually get captured by adjacent catchments, which are competing with each other for drainage area. So that was for the modeling. And what the model showed this contrasting behavior depending on the fluvial incision laws that we were using, depending on whether you used for threshold. And that allowed us to test and calibrate the models for the central Apennines.
So Mikael showed you really nicely what our numerical modeling suggested would be going on, but we also wanted to see, well, what do we actually observe in terms of an outcome in the field? So if you actually went to somewhere like this Fiammignano fault and the Rio Torto, then actually you see the real physical signature of transient landscape responses. You know, this is the long profile, elevation against downstream distance with this big oversteepen reach. So this nick point, if you like, actually corresponds with the top of this incised area. And in fact, actually, when you look at this landscape, you know, down here upstream of the fault, that's the zone of high incision, lots of landsliding, gorges, steep hill slopes. And then up here, upstream of the nick point, you know, it's low incision. The channel hasn't even realized that it needs to be incising more rapidly to keep pace with this faulting. So, you know, I mean, it was at the time, it was really exciting to be looking at this, exploring this with patients and actually seeing the physical embodiment of some of the modeling that we had been doing. And of course, actually, when we looked more widely in terms of the topographic analyses, what we were able to compare was, for example, all of the, the rivers crossing faults which had increased their slip rate. Those are the ones in red, compared to the faults that had a constant slip rate. These are the ones in blue, or those that are inactive, these dashed lines. So in fact, all of the rivers that cross faults with an increased slip rate showed this kind of transient response, which would be of a nick point upstream of a fault. Whereas all of these rivers that were crossing the inactive faults, they had these nice concave up long profiles. So one of the key things that came out of this, at least in the Apennines, was that in a broad sense, these rivers were consistent with a detachment limited model in terms of a response to changing uplift rate, or there or thereabouts. But also crucially, the landscape response time to tectonics in this area was between 1 and 3 million years, given that the constant slip rate faults, the rivers had adjusted to their existence over the last 3 million years. Now, that's just looking in terms of the topography. In terms of the actual field work, one thing that Patience and I talked about a lot was the question of channel width, because that was central to how we, for example, implemented the stream power, for example, in numerical models. And, in a general sense, we always end up saying, well, channel width is scales with something like drainage area, and actually it's something like the square root of drainage area. And if you look at many rivers, including some of these ones in the Apennines, broadly, actually, the data does obey that. But one of the key things that Patience and I got really excited about was the fact that if you compared predictions of traditional hydraulic scaling, width goes with the square root of drainage area, with what channel width actually does upstream of many of these faults, what we found was that width made the poorest predictions when it mattered the most. And actually, I can remember, I can remember producing this result and being quite pleased. And Patience was like, oh, we should definitely write this up for a geology paper. And she gave me, this is like basically the first paper I was writing. I got amazing advice about how to actually bring this together in terms of a story, because it made a huge difference to our calculations of, for example, unit stream power. This is stream power on the y-axis against downstream distance. And if you just use conventional hydraulic scaling, you would get a gradual increase of stream power towards the fault. Whereas actually, if you calculated the unit stream powers using the real measured channel widths, they're actually 3.5 times larger, much bigger increase towards the fault. And actually what we were able to argue was that this kind of dynamic channel narrowing actually was one of the key ways in which rivers managed to keep pace with active faulting, with a whole bunch of implications about when and where sediment reaches deeper centers that we'll come on to.
So the last main outcomes that we wanted to introduce here was the somehow unexpected outcome was the role of sediment in modulating the landscape response tectonics. So as we had done all this work in the Apennines, we are thinking, okay, that applies there. It would be good if we had other areas that showed similar response to show that this model is widely applicable. And Patience and Gerald had a colleague at Anassos Ganas in Greece, who just said, I know a place where you can test that. So here we have the Rio Torto, which is flowing across the Fiaminiano fault. And he said, well, the Xerias River flows across some faults. They have a very similar history, like the flow rate on the fault has increased around 1 million years ago, although to a lower extent, like the rates are not as high. The climate is similar, the catchments are a similar size, the river is incising into limestone like it's there. And look at the DEM, there is a nick point. We're just like, okay, great. Well, let's go there, and it would be good to have a comparison here. So I do remember driving here, stopping somewhere around here, and walking up that gorge to find that nick point. And indeed, there was a gorge. So the river was clearly incising into the limestone, but there were no nick points. Like that nick point that we had seen was just an artifact of the digital elevation model, just because it was not able to pick the gorge at the channel at the bottom. But what was really striking was really the bedrock was barely exposed on the riverbed here. Like most of the riverbed was covered in sediment, pebbles of a range of size. And when we reconstructed the river profile from our measurements in the field, this is what it looked like. So here we've got two river profiles, the Rio Torto and the Xerias River. And they had both very similar histories, but the response is very, very different. And that's when we started really trying to explain the main difference between these two catchments. And that's when we thought that, and we made calculations to back that up, that the difference is essentially due to the role of sediment. Because in the upper part of the Xerias catchment, the river is incising into these poorly consolidated conglomerates. And they're just made up of perfectly rounded, they're beautiful, perfectly rounded, perfectly sorted, igneous and metamorphic rocks, so very hard pebbles. And the river just picks these pebbles and transports them downstream without too much effort because of the perfect sorting and so on. And that's in contrast with the upper part of the Rio Torto, where because of the, like where we observed that because of the uplift and the back tilting, we have low gradient, low relief areas. We've got low gradient hill slope. It's essentially soil mantled, and soil is being supplied to the river, and there's barely any sediment that the river is transporting. And the sediment will be limestone anyway, because so the contrast in rock resistance here, we think that because that river has to transport these pebbles make excellent tools for erosion. And just by taking these pebbles from here and transporting them across this zone of high uplift, the river is able to counterbalance the effect of the increase in uplift rate and that leads to a very different expression of active tectonics in the landscape. So here the sediment flux and the sediment grain size control the response, the style of the response to tectonics, with the Greek example being closer to the transport limited end member, and the Apennines example being closer to the detachment limited end member. So where has all this led? So we're going to take a few directions here. Well, there's tectonics from topography, but we've decided that, well, Alex and I can probably spend 2 days talking about that, and you don't want that. So we've decided to focus on a few points. And the first one is really carrying on with that sediment sourcing, release, and grain size. So at the catchment scale, from the hill slope to the river. Then thinking on a broader scale about basin implication and drainage network integration. And then the deeper implications and how we can use like the topographic expression of fault to gain some insight into lithospheric behavior and seismicity. And that's what we're going to talk about in the next few minutes. And I'm going to talk about sediment sourcing first. And so that's some work that we carried on doing in the Apennines. That was during Alex's postdoc with Philippe Allen in London. And what we wanted to know is how the changes in topography that we can see downstream of this nick point, where the faults have increased their uplift rate. We've seen this steepening of the river, steepening on the hill slope, a lot of landslides, and here we've got the depth of incision. And we wanted to know how that was influencing the characteristics of the sediment in the river. Why are we interested in that? Because the characteristics of the sediment in the river, like the grain size and the flux, that's going to control the fluvial incision rate, is going to control habitats locally, and it's going to control essentially the characteristics of the signal that are going to be recorded in sedimentary basins. And what we showed here is that the sources were having a very significant impact on the grain size of the sediment that was transported in this river. So here, for example, we're going downstream in that direction to the right. We've got the median grain size, D50 in white, the D84, the 84th percentile in black, and that's along these two rivers. And what we can see is that in the zone of steepening here, which is shown in gray, the grain size increases massively by up to an order of magnitude, just essentially as a result of landslide providing coarser sediment to the river. So that was like there was not that much focus on the source of sediment at the time, and being able to demonstrate that something that is quite obvious but needs more attention was very important. If you've got more landslides, you're going to supply coarser sediment, and the rivers are going to export coarser sediment to the sedimentary basins. Again, we gained that knowledge about transient response tectonics. We gained that knowledge about a source of sediment, and we wanted to explore that a bit further. And that's some work I've been involved with Martin Hurst and Simon Mudd. And in that case, we went to California, where there is a clear wave of incision that is propagating along the Feather River, which is here in California. And we wanted to see if that like source of sediment signal was present there as well. The advantage of that place is that the lithology is homogeneous. It's granite. And we really see the contrast, like the contrast is quite impressive between this relict landscape, where you've got a low gradient river, low gradient hill slope, low relief, and then downstream of this nick point that's propagating upstream, so the plateau is being progressively dissected. You've got steeper river and a lot of landslides, for example. And what we were able to show in particular was this very distinct behavior in these places, where on the plateau, the sediment that the river transports, the grain size of the sediment is limited by the grain size of the sediment that supplied the river. There's mostly soil mantle landscape supplying very fine grain sediment. And even if the river had a lot of power, they will not be able to transport large clasts because there are none. So here, that was a place where the grain size of the sediment transported is supply limited. And that was in big contrast with what you can see in the incised part of the landscape, where many landslides and rockfall are bringing sediment grains of all sizes. I mean, there is a person from scale here, and you can see these blocks that are the size of a Honda Jazz that the river may transport very occasionally. And so here, the grain size of the sediment transported by the river is going to be essentially set by the flow, the competence of the river, what the river has the ability to transport. So that was something that we were able to demonstrate further. And at the moment, there are a lot of studies that are focusing on the source of sediment and grain size in particular, and that's very exciting.
So while Mikael was inspired to go to the US, one of the things that I really wanted to take away from my work with Patience was to explore further the interactions of tectonics and erosion in Italy. And one of the places that we went to do that was actually down in the southern part of Italy. And this is some work that I did with my PhD student, Duna Roda-Baluda, and she did an amazing job of really understanding how active normal faulting is coupled to landsliding and erosion and sediment export in a bunch of these catchments. And one thing that had really been developing since I had started to work with Patience was our ability to actually quantify catchment erosion rates using cosmogenic nuclides, and that's one thing that Duna really led. And one of the questions we had for this part of Italy, if this will advance, is to actually really try and test the question of, do our catchment erosion rates actually scale with fault uplift rates as you might expect? So actually Duna and I collected a whole bunch of data along the strike of these faults in here. And one of the things that we were able to ask questions were things like, for example, do we have faster erosion rates in the center of faults? Do we have slower erosion rates upstream of nick points in some of these transient landscapes? So these are the kinds of questions that we wanted to ask, inspired in part by some of the work that had been done in the central Apennines. So whilst many of the fault slip rate catchments crossing faults had rates of 0.2, 0.3, 0.4 or more millimeters a year, we were particularly also able to show that many of our and other people's sample sites in the uneroded, unincised upper landscapes of this part of southern Italy, it all had low background erosion rates. And actually, one of the cool things we're able to show when we actually compared erosion rates with footwall uplift rates along strike was that for many of the samples that we got, that actually our catchment erosion rates were comparable to our tectonic rates, as you might hope if you buy some of the work that we had been doing in the central Apennines, but also some of these open circles. I'll just go back. These are catchments upstream of, these are sample sites taken upstream of nick points. These are the ones that uniformly had the low erosion rates. So actually that coupling, demonstrating that coupling between active faulting and catchment erosion that we and other people are doing have been really important development, I think, in the last few years. So one of the things that comes from this as well is that if you've got good constraints on how rapidly catchments are eroding, and as Mikael has demonstrated, you can work out some indication of the grain size distribution of that material, then actually you can compare the grain size that is being exported with the amount of sediment that's coming out of these catchments. And one of the things that we've been looking at is, in fact, that for many of these, as you increase the erosion rates and the sediment fluxes, you also increase the average or the coarse fraction grain size that is being released. So in this sense, one of the, we could identify 3 effects of catchments responding to tectonics. One is in terms of an increase in sediment flux, but we also have to think, in fact, in terms of the changing sediment sources, particularly the development of landsliding in steep incised zones upstream of faults in the nick zones. And we also get a change in the sediment grain size distribution. And the recognition of these 3 things has really important implications for understanding basin stratigraphy. And this has actually been one of the, I was inspired from working with Patience to then move on to tackle this question. And one way we did that, and this is work with John Armitage and Rob Duller and Philip Allen, was to actually try and couple catchment models with stratigraphic models. So for instance, we took a simple catchments that in this case, we were going to erode using nonlinear diffusion in this case. We actually coupled grain size release to some of the field observables that we've just seen from Italy. We scale the catchment basin tectonics to the right setting, in this case, a normal fault. Actually have a look at what we would expect to see in the hanging wall stratigraphy of that normal fault using a mass balance approach, and then find the grain sizes that we are inputting, in this case using a self-similarity grain size finding model, which is another thing that I've been working on in the last few years. So what I'm going to actually show you is actually this, not the catchment end, just what you see in the basin. And these are runs that are scaled to the Fucino Basin in Italy, where we basically run the model to steady state and then look at a perturbation, in this case, a 5-fold increase in fault slip rate. And that's along this stratigraphic timeline here, where this is distance, this is depth in the basin, the color is the grain size, so green coarse, red over here, fine. So when we increase the fault slip rate in this case, we do get coarser sediment coming in. That's because of the geomorphic effects that Mikael has outlined. But that sediment fines very rapidly because it takes time for the catchments upstream to erode enough sediment to fill the basin where that accommodation is being created instantaneously. So the effect of that's quite profound. So if we looked at a borehole through this part of the stratigraphy, at the point where the fault slip rate increased, column A, we would get a coarsening in the predicted stratigraphic grain size, whereas along the same timeline in column B, we'd actually get a fining. So a lot of this work has challenged our, I guess, some traditional interpretations of how we would look at hanging wall stratigraphy. And I think the key thing that, I would emphasize is that, if you believe in, let me go back. If you believe in transient landscape responses, we also need to believe in transient stratigraphy. And that's something that's really come out of the last 10 or 15 years worth of work. Related to that is actually something that Patience was really pushing forward in Bergen with her PhD student Elaine. And what they were really working on was on this larger scale, trying to understand how drainage integration would actually affect when and where you get sediment being sourced to basins. And this is some work that Elaine really led and drove forward. And she actually showed by essentially coupling a fault model with Cascade, which is a landscape evolution model, that essentially basin filling and overspilling in the Italian Apennines actually drove the integration of drainage basins. And that process was more important than headward erosion in terms of moving from internally drained basins, that's this sort of greenish color here, which shrank over time, to more externally drained conditions. And one of the final things we were involved in together was to actually then really try and, this is a model, but actually see whether or not field data from some key catchments in the Italian Apennines actually supported this kind of behavior, which they largely do. So yeah, I would recommend this geomorphology paper of Anne Lane's if you want to read the full details of that. Now, we've talked about some of the stuff that Mikael and I did inspired from Patience's work. I want to come back to what did Patience do next. Well, one of the things that she got really interested in was actually to try and understand further fault slip histories in places like the Italian Apennines. And I actually see this as something that has almost come full circle, in the sense that, she started looking at the evolution of faulting, and then we all got interested in how did faulting couple and drive landscape evolution. And in this final part, really we start to learn about how geomorphology or landscape studies can actually give us deep insights into the behavior of faults and the behavior of the lithosphere. So, one thing in a big project that Patience is involved in, and with many others, including Gerald Roberts and Laura Gregory, was to actually really understand fault slip histories from chlorine 36. And actually, if you measure this up a fault scarp, you can basically sample a bunch of points, and there's a lot of detail, a lot of modeling that goes into this. But in principle, you can produce predictions, this is height of fault scarp against the chlorine concentration. You can produce predictions of what the chlorine concentration should be for a range of constant slip rates on some of these faults. And that's what is shown here from Patience's scientific report paper. And of course, that can be contrasted with what do we actually see on a bunch of these faults. This is the Fiumignano fault. That's the one that Mikael and I have talked about a lot today. There's a bunch of other faults in here. And some of this data is really interesting in the sense that it supports the general idea that some faults are moving rapidly and some faults are moving more slowly. But it's also interesting because not all of the data lie on essentially lie on lines that would be consistent with constant slip rate in the last 15,000 years. And actually one of the, the things that Patience has been working on was to actually then say, well, what does that imply about the modeled slip history of the faults? And actually what it implies is that some faults move rapidly for a few thousand years, and then they move slowly whilst other faults take up that strain. So this is actually quite profound, and it's work that is carrying on at the moment, because it actually really gets to the heart of earthquake clustering and the averaging of strain over the seismic cycle. So I think this is something to watch, and I think this is where the science is going at the moment.
All right, and I'm going to finish with another study that by Patience and her team, which was really like I didn't understand its significance when it came out, and then I started teaching structural geology with my colleague Florian, and I was just like, wow, this is amazing. So the idea is that rocks, when they deform at depth, they're deforming with that viscous flow. And there's supposed to be a power law creep. And essentially what that's showing is that if you've got, here we've got the stress, so that's the force that you're applying to your rock divided by the area of your rock. And this is the strain rate. So that's how quickly your rock deforms. And we have logarithmic scale here. And what the theory says is that when you're in that moderate stress regime, there is that power law with an exponent of around 3 here, which shows that how the deformation rate increases as you increase the stress under which you put your rock. Most of that data is theoretical. That's experimental data from Olivine. Other rock types are showing similar trends. And that paper by Patience and colleagues came out in 2013, and it's called Viscous Roots of Active Seismogenic Faults Revealed by Geological Slip Rate Variation. So the idea was simple, is let's imagine that the faults in the Apennines were made of 2 components, a frictional component, which is the part that's brittle here at the surface, and that connects to a viscous component, which is that monolithic shear zone here. So we have that simple model. And what we want to do is get the stress and the strain rate. Well, the strain rate, we can get that from the fault scarp actually. And you can calculate that, you can measure and calculate that across all the Apennines. So you can measure the amount of deformation that there has been. And because you know that it's been in the last 15,000 years, you can get a rate. So that's one part of the data. And the second part is modeled, making assumption that the elastic brittle, the upper crust, is at yield, which is a good assumption as there are earthquakes there. So we know that it is at yield. And that sigma 1 is vertical, which also applies to areas in extension. So you make this calculation of stress, and this is what comes out of this relationship. So the strain rate is from the fault scarp, the stress is from the calculation from the model. And here you've got the data with an exponent of 3.2 to 3.3. So I just thought that was a very elegant demonstration of how you can use topography to learn about the deformation deep in the lithosphere. So their conclusion at that time was, although we cannot rule out some distributed deformation, we suggest that fault strain and thus earthquake recurrence in the Apennines is largely controlled by viscous flow in deep localized shear zone over many earthquake cycles. So looking at what's happening to the fault scarp, looking at what's happening at depth, and you get a greater understanding of how the lithosphere deforms, which can then inform our seismic hazard approaches, in particular for tectonically active areas like the Apennines. And on this note, I'm just going to finish. These are, Patience didn't like us to take pictures of her, so we don't have that many pictures, but I mean, putting together this talk has been wonderful because it reminded me of the great time we had there. That was some of my best time in my career. Like working with Patience was brilliant. She was really encouraging, she was positive, supportive, excited about everything pretty much when it was about science. And she was also very critical, but knew how to tell you when you had a good thing, when you had done a good thing. So yeah, it's been a fantastic experience working with Patience, and she's been a role model for many of us, and I'm really grateful to her.
Yeah, I mean, I think, you know, I think I truly feel, you know, formed as a scientist in a way. Going to work with Patience really taught me how to think, how to really carefully work through a problem and make sure that it was properly understood and that you actually really tackled the question in a forensic way. But you know, more than that, you know, I think I really benefited from Patience's mentoring and actually deep interest in making sure that, you know, not just during my PhD, but afterwards, that I was making progress and that, you know, my science was on track. And I, you know, I can't thank her enough for that. And, you know, the PhD and the subsequent work has been really, you know, fun as well, which has been one of the most important things.
And we took 1 hour, Alex. I'm really sorry. Sorry.
Oh, well, never mind.
But thank you very much for your attention.
Yeah, it's been an honor to do this.
All right, thank you, both of you. This was really great. I'm so happy that I got this overview of Patience's work from you two. And now we've opened the chat, so everyone can ask questions, add comments, and I'm sure the two of you will do what you can to answer. And I'll also ask Steffi and Philippe to turn on their video and take part in this in moderating the discussion. And so while we wait for the first questions to arrive, it started already. I'll still manage to ask mine first. So this change that you saw both actually in the Apennines and in Greece that happened about 1 million years ago, why did this happen? And what's your opinion about that?
You mean the change in fault slip rate?
Yeah, exactly.
So, yeah, I mean fundamentally the change in fault slip rate in the Apennines, Patience would say that had been driven by fault growth and interaction. The interesting question is, of course, how long does it take for faults to grow, nucleate, and start to get to the point where they can interact even in a soft linked way across a fault array? And, you know, our models would suggest that, you know, it takes a while for that to get going, and then suddenly these faults then really start to speed up. You know, the Greek examples, actually, the timescales are a little bit less well constrained. I mean, the Zerias River that we were presenting runs across the Arkitsa-Nimis fault segment boundaries, and those faults that are coming down that part of the Gulf of Evia are really part of this larger Spercheios graben that's got a slightly longer history. But exactly why it happens at that time, that's a good question, and I think it takes time for essentially for the interacting stress fields to really get to the point where the faults really start to go, because we also see around that time that a bunch of these faults towards the west also die.
Yeah, I'm not going to add anything. I'm in that.
All right.
All right.
Steffi and Philippe, do you want to take over with the questions from the chat?
Yes, also first, thanks a lot from my side. It was really nice summary and overview talk you just gave. Nice to honor her contribution. So the first comment in the chat is not a question, but actually a comment from Hugh Sinclair. I'm just going to read it out so that everybody knows. Thanks so much to Mikael and Alex for presenting so clearly the way in which Patience's work has acted as a pillar for ongoing fundamental studies. I'd like to follow this by announcing a further celebration of Patience's career at EGU in 2021, where we have a union symposium entitled Faults and Tectonics in Memory of Patience Cowie. And there's also a list of speakers. Is Chris Scholz, Zoe Shipton, oh, the next one is tricky for me to read, Sophia Pechlin-Vandio, I hope that was correct, Philip Steer.
Close enough.
Thanks. Joanna Walker and Alex Whittaker. Okay, but then I might just continue with the first question that we got in the chat. Also, again, thanks for the talk and an excellent tribute to Patience. I have a general question. What you presented was landscape response to normal faults. Are you or anyone else addressing these questions to other fault types?
Yeah, I guess, I mean, the field of tectonic geomorphology has really exploded now that you've got DEMs from anywhere in the world. And I think, yeah, there are a lot of studies in like active mountain ranges, like where there's compression, a lot in the Himalaya. Luca Malatesta talked a bit about, was one of your speakers a few weeks ago, talked about some of these studies in the Tian Shan. One place where there's not much going on is a strike slip fault. I think they're a bit difficult to understand. I know that Greg Tucker has had some collaborators who worked on the Alison Duval did some work, for example, on the morphological expression of strike slip fault. But I think, yeah, strike slip fault, not so much. Compressive settings, yeah, there is a lot going on in the Andes as well, using tectonic geomorphology to try to get tectonics from topography.
Yeah, I mean, one of the nice things about normal faults actually is that the uplift field in the hanging wall, in the footwall and the hanging wall substance are relatively easy to model. And in compressive settings on a thrust, actually, you have to make some choice about, is this a single step fault propagation fold or something if you really want to model the uplift profile in the hanging wall, and therefore that makes it structurally harder. But yeah, loads of people are working on this now.
But yeah, I totally agree. It's like, yeah, the fault geometry is much harder to resolve in these cases.
So there's a question from Simon as well. How do we know that the faults in the Apennines accelerated? Yeah, so the answer to that question is in terms of the Basin stratigraphy. So we actually have got, so say for the Fucino Basin, for example, we've actually got seismic data, we've got boreholes. So there's actually a long history of faulting in there. So you could read, for example, a paper by Cavanato in the early 2000s that goes through that. And then subsequently, Anne Lane, Patience's last PhD student, actually did a bunch of work actually as part of the work I was telling you about in terms of the drainage integration, really looking at detail at the basin fill stratigraphy for a bunch of these basins. Now, dating, in some parts, dating continental deposits is tricky, but in fact, there's a wider history of fault evolution in the Italian Apennines, including a bunch of now dead normal faults out towards the west. So we actually have a relatively good idea about that stratigraphic evolution, at least since the Miocene.
By the way, do you want me to stop sharing? So that people
leave up the photos of Patience.
Okay, right.
It took us ages to find them, Mikael. I had
That's
to
true,
scrutinize photos from 20 years ago.
And I think once you stop sharing, we just basically see the video screen. So
yeah,
okay,
it's
all
fine
right.
to leave them on. It's a lot nicer. I would just like to use this moment to ask a question myself, because I was quite impressed again by these two river profiles that you were showing, the one from Italy compared to the one from Greece, and that look quite different from one another. And maybe you said it and I just didn't hear it, but the fault rates, were they basically similar, or was the slip rate actually less in Greece compared to Italy? And maybe as a follow-up question, have you thought, or you probably have, but what could have been any other explanations? Or have you thought about other ideas that could explain this fundamental difference that you then kind of, could reject after some further testing?
Well, so the first, like the flow rate was, no, it was less than half on the, so I think am I wrong? I think it went from 0.2 to 0.4 millimeter per year on the acceleration, Alex. I think that was.
Yeah, that sounds about right. I did a little bit more work on it with a master's student of mine, but yeah, the rates are probably half of
the
rates were less, although the bedrock geology was broadly the same.
In terms of alternative explanations, I mean, that was the most obvious to us, and because like from when we started thinking about sediment, we did calculate the sediment fluxes, and we saw really how much difference there was between the catchments in Greece compared to the ones that had the conglomerate compared to the one in Italy. Like we could back that up with calculations of sediment flux. In terms of alternative explanation, yeah, we were not too sure what else we could invoke. Like as we said, like a lot of the things are similar. The climate is similar. The hydrology of the river would be similar. The bedrock was very similar as well. So, I mean, do you have any suggestions?
No, it's not that I have a fantastic idea now. It was just that they were so incredibly different, although you would expect them to be somehow similar, that it was quite stunning.
Yeah, we were looking for that Nick point.
Yeah, it was not what we expected at all. I mean, I think that what we now, one of the things, I mean, Mikael didn't show it, but we actually, in fact, we ended up contrasting a bunch of rivers in Italy with several in Greece. And it's this idea that it's either, like right at the detachment limited end member, or it's sort of more diffusive. There's this whole spectrum of sediment flux dependent incisions in between, which we could place those channels into that context. And I guess for me, that was, it was an introduction to realizing that life was not as simple as a stream power law.
Okay, I guess that's a nice roundup of the question I initially asked. So maybe, Philip, do you want to continue with the next one?
So thanks very much, Alex and Mikael, for your talk. It was really great.
Well, thank you for the invitation.
By Cowie, I'm sorry if I don't pronounce it correctly. How can we distinguish hard and soft linkage of normal faults?
Yeah, I can answer that. And there's relatively straightforward. So when faults are hard linked, they are physically joined. And in that case, you would expect to accommodate or accumulate displacement at paleo segment boundaries. So what was the boundary of two fault segments? That fault tip is now part of the longer fault, and it would undergo a significant throw rate enhancement and gather displacement. In contrast, when faults are soft linked, the individual fault segments do not physically join, but let's say the segment in the middle knows that detects the wider strain field, so it slips more rapidly, but it does not have to be physically joined to neighboring segments along strike. And that means basically the fault tips remain having zero displacement. And when you get these soft link faults, it also therefore implies that you have very substantial tip to center of fault displacement gradients.
As you said.
Okay, then I just follow up with the next question from Yu Chun Chang. Hi both, thanks for the brilliant talk. I wonder whether this analysis approach can somehow work in submarine settings, or any difference or challenge we need to concern in submarine area.
Yeah, I mean, I can try to respond to that. So I think the first one I would say will be the availability of data. We've got topographic data of the world freely accessible, so it makes this sort of analysis on land much easier. In submarine environment, I think what makes it difficult is that the whole framework that we tested was based on an understanding of erosion processes along rivers and the assumption that you're going to try to go towards steady state. So erosion rates are going to try to counterbalance the effect of uplift. So rivers are going to respond one way or another. And we've got an understanding of the erosion processes in rivers, whether it's abrasion, plucking. In submarine setting, it's much more difficult to understand how that works because I think we don't have that background physical understanding of the processes that lead to erosion. for example, and we tend to think more about deposition. So I think we can learn a lot about what happens in submarine setting. And I know that Alex, for example, did some work in the Gulf of Corinth with one of his PhD students, where they looked at the signature of the sediment deposition in the submarine environment. But I think it's much harder to apply that framework we presented like identically to submarine setting.
Yeah, it's a challenge. I've actually been trying this with seismic data in the Niger Delta in the Gulf of Guinea, where we've basically taken the seabed seismic imagery and actually looked at submarine channels interacting with growing folds and thrusts. But Mikael is exactly right in what he says, in the sense that what we don't have is a right down turbidite erosion law. And one of the big uncertainties is that we don't understand really the frequency of turbidites. But actually that work's been showing really interesting stuff in terms of submarine channels don't do what rivers do. So for example, you don't get that dynamic channel narrowing at the element scale, but you do get entrenchment of the submarine channels upstream of these growing fold thrusts. So actually this is something that's in its infancy at the moment, and this is new work that I've hooked up with some of my seismic colleagues at Imperial, but it's been exciting to work on something that I don't really know about, so it's been kind of good.
So we have a next question by Antoine Delaunay. I think he's referring to the difference between the Italian and the Greek river. So it will mean that once all the conglomerates are eroded, we should start to have a nick point. Maybe it will be interesting to compare river profile in the same region, similar uplift, but with different lithologies, coarse versus fine.
So I guess, yeah, technically that is true, except if the uplift rate has increased. The river has probably been adjusting its gradient, but in a more diffuse way, like in a more transport limited system. So if for example, the relief increased without any need for nick points, and by the time you run out of conglomerate, like the river has reached a profile that allows it to cut at the same rate than the uplift, then you may not necessarily have a new nick point creating. But if not, and actually you may think that the change in sediment supply will probably have a big influence on the erosional capacity of the rivers. So in that case, yeah, you would expect potentially a nick point to start. Actually, I'm not aware of many studies that have looked at how a change in time of sediment supply could influence the river morphology. But I guess, yeah, you will need an understanding of how this sediment supply is changing through time and how this river profile is changing through time. So I think the difficulty is finding the good place to test and answer these questions. And I think, for example, in the Greek area we're talking about, I don't think there are that many places where we've got constraint on faults and faults that have accelerated. And we didn't have that many catchments that could really compare to directly. I think that was the difficulty, was finding suitable catchments. But yeah, if you're interested in pushing further with that, go for it.
I think there is a nice paper by Malatesta and Lamb in 2018 at Geology that considers this issue.
Right, okay. Thanks. Alex, did you want to ask?
No, I think you said it all.
Okay, good.
Okay, so I think it's a last chance. If somebody has a question, it has to go into the chat quite quickly now. And otherwise, I'll just thank you again, Alex and Mikael, for this great talk. And also congratulations on this successful joint presentation that you gave. It really went very smoothly. It's the first time I've seen that in Zoom.
Well, so... our first practice one was not quite so smooth. We had to do it a few times.
Okay. Yeah, well, we appreciate that you did that.
Well, thank you very much for the opportunity. I mean, it's been really a challenge, a privilege, sorry, a challenge technically, but a privilege to actually give that presentation. So I think there was a question, the last question that came just in.
Yes, exactly. I'm going to read it out to you.
Okay.
In case of a normal fold, 10 beryllium erosion rates have similar magnitude to fold throw rates. Then how about a thrust fold? You think do you think that the same interpretation can be applied to the thrust-related landforms?
The answer is in principle, yes. It's just that you have to think more carefully about the distribution of uplift in the hanging wall of a thrust. So a lot of these interpretations are applicable to thrust faults and to convergent settings, including the Himalaya and the Andes. It's just the numerical modeling and the field observation is easier on a scale of a normal fault block, but that means that you can of course do it in convergent settings, and with certainly lots of people have.
Yeah, I think what I would say about the thrust fault is that usually, I mean, from what I've seen in the Apennines, you've got a thrust, you've got an earthquake, you've got an offset, and then it degrades, and then it gets buried in sediment. So you don't preserve thrust fault scarp as nicely as these ones in the Apennines, which I think were really spectacular. But otherwise, yeah, the theory could apply technically. Thanks for the question.
And we have Antoine Delaunay, I think, that continue on the issue of eroding conglomerate. So he's now referring to the Red Sea, where the Cambrian sandstones could have been eroded only partially on the Arabian plateau. So it's just a suggestion for looking further to this issue.
Okay, well, I'm not aware of this area, but yeah, if you know a good place to test that, definitely up for that. Thank you.
All right, thank you everybody for the questions, and I think it's also great to hear that we will have another celebration of Patience at EDU in the coming year. So hopefully we'll see each other then, also virtually like this. But yes, so thank you everyone.
Thank you very much.
We're done for today now. Yeah.
Okay, thanks. Bye everyone.
Goodbye.
Thanks a lot. Bye-bye.